Last video I published was about angle trisection, and I got a comment from New01000 where he proposed a different solution to that problem, and I like that solution a lot, so I decided to use it to investigate this problem a little bit more details. So first of all, we're gonna have a similar problem but not exactly the same. We're still going to have a right triangle ABC. We're going to trisect angle B by segments BD and BE. And that means that those segments split the angle B into three congruent angles. And those segments are going to split the side AC into three segments. But now we're going to say the lengths of those segments are A, B, and C. And we would like to have all A, B, and C be integer. And the question what we're going to ask here is, what would be the minimum values of A, B, and C we can have? First of all, let's call the length of AB is D, length of BD is E, BE is F, and BC is G. There's obvious relationship between those lengths. D will be the smallest one, E is bigger, F is even bigger, and G is going to be the biggest one. That seems to be an obvious fact, but nevertheless, let's just prove it once and for all. First of all, let's look at the right triangle ABD. We can write a Pythagorean theorem for that triangle. And notice since a squared is positive, d squared plus a squared should be greater than just d squared. But now notice that e squared is greater than d squared. And since both e and d are greater than 0, that's only possible if e is greater than d. So what we show here is that hypotenuse of a right triangle is always greater than any leg. But how do we show that F is greater than E? Well, to do that, first of all, let's look at the right triangle ABE and write Pythagorean theorem for that triangle. And now we're going to subtract the first Pythagorean theorem from the second Pythagorean theorem. And that's what we're going to get. Obviously, the first term on the right-hand side is greater than the second term on the right-hand side. So the right-hand side is greater than 0. But that means that left-hand side is also greater than 0, and f squared is greater than e squared. And since both f and e are positive, it means that f is greater than e. In a similar fashion, you can show that g is greater than f. And here we're going to have that relationship we were looking for. We need this relationship to actually find the relationship between A, B, and C. And now we are ready to do that. First of all, let's look at this green triangle. Triangle ABE. In this triangle, BD is an angle bisector. And every time when you see angle bisectors, you should think about angle bisector theorem that says that the ratio of the segments AD to DE equals to the ratio of the sides of this triangle, AB and BE. Another way we can write this expression like this. Now we just show that D is less than F, but that would mean that A is less than B. Now let's consider this yellow triangle DBC. BE is angle bisector. Again, we can apply angle bisector theorem here. DE to EC should be equals to BD to BC. And again, if you look here, we find that E over G has to be less than 1 because E is less than G. And that means that B has to be less than C. And if we combine these two inequalities together, we get what we're looking for. A should be the smallest one, B is bigger, and C is even bigger. And now we have this relationship, so we are ready to tackle our main problem. First of all, we want to do additional constructions here. We're going to take this gray triangle ABD and reflect it over the side AB. We get triangle ABF. And obviously angle B here and angle B here are congruent. BF should be congruent to BD, and AF should be congruent to AD. And now let's consider this big triangle FBC. In this triangle, BD is angle bisector. So we're going to apply angle bisector theorem here, which means that FD to DC should be equal to BF to BC. And now we're going to consider yellow triangle DBC. BE is angle bisector. We're applying angle bisector theorem that gives us this relationship. Now look at this guy and this guy. And notice that the right-hand sides are the same. That means that the left-hand side should be the same. And this gives us the relationship between sides A, B, and C. Now we're going to play with this a little bit. We're going to get rid of denominator, combine terms, and this what we're going to get. Notice the left-hand side is positive. That means the right-hand side has to be positive. But that means that the parentheses have to be positive. And that will happen when 2a is greater than b. But we already know that b has to be greater than a. And that means that b has to sit between a and 2a. And now let's try to find the minimum of a, b, and c. Let's start with a. Obviously, what is the smallest integer we can have? It's 1. So let's try 1. A equals to 1. Does it work? Well, let's look at this inequality. If we look at it, we find that in this case, b has to be strictly greater than 1 and strictly less than 2. And also it has to be integer. Well, there is no such a b. So 1 doesn't work. Let's try 2. When a equals to 2, the same inequality gives us that b has to be greater than 2 and less than 4. There's only one b like this, and that is b equals to 3. And now if we take this a and b, plug in this equation, we're going to get that c equals to 9. So indeed we find a solution for a equals to 2 and b equals to 3 and c equals to 9. But it also tells us that the minimum value of a we can have is 2, and minimum value of b we can have is 3. But now the question is c equals to 9 a minimum value for c or not? Do the minimum values of a and b correspond to minimum value of c? If you've seen the previous video, you know the answer. But here we're just gonna get it. So we know already that c equals to 9 is possible. So what we want to try now is values of c which are lower than 9. So let's start with c equals to 8. Now if we have c equals to 8, we plug it in this equation. We get expression like this for b and a. Notice here that b squared is divisible by 8. Well, technically, if b squared is divisible by 8, we know that b squared has to be divisible by 16, and that means that b has to be divisible by 4. But let's just move slower now. Well, if b squared is divisible by 8, we know that it's divisible by 4. But that would mean that b itself is divisible by 2. Now notice that minimum value of b is 3, and b has to be less than c, which is 8. So the only value of b that is divisible by 2 and satisfy those two conditions is b equals to 4. Now, if you plug c equals to 8, b equals to 4 right here, we can easily find that a has to be 3. And as you can see, we found the solution for c equals to 8. And that means that the minimum value of c does not actually correspond to the minimum values of a and b. We know that minimum value of c is no more than 8. But could it be less than 8? That's really the question. So let's check it. Let's check c equals to 7. Again, plug 7 into this equation. That's what we're going to get. Now we see that b squared is divisible by 7. 7 is a prime number. We can't split it into factors. But that means that b itself has to be divisible by 7. But now notice that b is divisible by 7. The minimum value of b in this case will be 7. But we know that c is equal to 7 and c has to be greater than b. So that tells us that, well, there's no solutions. It's not possible. Next thing, let's look at b equals to 6. In this case, we're going to get this expression for a and b. We see that b squared is divisible by 6. 6 is not prime. It could be split into 2 and 3, which are prime, which means that b squared is divisible by 2 and by 3. But that would mean that b itself has to be divisible by 2 and 3. It means that b is divisible by 6. The smallest b possible is 6. But again, it's a problem because c equals to 6 and b has to be less than 6. Again, that doesn't work. In a similar manner, we can show that c equals to 5 doesn't work. And really the only case we need to check now is c equals to 4. Notice that c is greater than b, which is greater than a. And also we know that minimum value of a is 2, minimum value of b is 3. So if you want c to be 4, the only option we have is for a to be 2 and b equals to 3. But previously we said when a equals to 2 and b equals to 3, c equals to 9, not 4. So that case doesn't work as well. And here we have it. We just show that the minimum value of c we can have is 8. And we solve the problem.